Chapter 11 covers self-balancing search trees. Now, the objectives of the chapter are to understand the impact that balance has on the performance of binary search trees. We'll learn about the AVL tree for storing and maintaining a binary search tree in balance. We'll learn about red-black trees. We'll learn about 2-3 trees and 2-3-4 trees and B trees and how they achieve balance. And to understand the process of search and insertion in each of these trees and to be introduced to removal. Now, the performance of a binary search tree is proportional to the height of the tree, or the maximum number of nodes along a path from the root to the leaf. A full binary tree of height k can hold 2 to the k minus 1 items. Now, if a binary tree is full, it contains n items, the expected performance is order log n. If the binary tree is not full, the actual performance is worse than expected. So to solve this problem, we introduce self-balancing trees to achieve balance so that the height of the right and left subtrees are equal or nearly equal. And we'll also look at non-binary search trees, the B tree and its specializations, the 2-3 and the 2-3-4 tree. So let's start with tree balance and rotation. Now, why is balance important? Searches in an unbalanced search tree can be order n, worst case, and not log n. We saw earlier in the semester, if we have a tree where everything gets added to the right subtree, it turns into a linear list. Here's a realistic example of an unbalanced tree. When we build a tree and we always insert at the leaf, then the order that things are inserted can dictate the shape of the tree. Now, we need an operation on a binary tree that changes the relative heights of the left and right subtrees, but preserves the binary search tree property. Okay, and these are going to be rotations. Notice this left tree is not balanced. But if we do a rotation around the root of the tree, so that we take this node 20 and rotate it so that it's the right subtree, and bring up 10 to the root, we can get a tree that's close to being balanced. And the interesting part is we've got to take this 15, which is a right subtree of 10, and adjust it so it's now the left subtree of 20. And now the heights of the left and the right subtrees are the same. Let's look at an algorithm for rotation. So here's a binary tree with the root being 20. So the algorithm is to first remember the value of root arrow left. Okay. So root arrow left is a pointer to the node containing 10. So we'll assign that to temp. Then we set root arrow left to the value of temp right. Okay, so that modifies this pointer. So now that 15 is the left child of 20. And then we set temp right to be root. Then we can set root to temp. So now 10 becomes the root of the tree. And that's how we get a tree that's more balanced, and we did the adjustment so that 15 is in its proper location in the binary search tree. Now, to implement rotation, here's some UML diagrams that build on what we've seen earlier in the book. Here's our binary tree, and then a binary search tree is a specialization of that. And then we'll create binary search tree with rotate, where we'll have a rotate left and rotate right method. And our binary tree consists of nodes that contain data and then left and right subtrees that are themselves nodes. So here's our recursive data structure. Here's some code to implement rotation. So we have a class BST with rotate, and we have a rotate right method where the local root is the root of a binary search tree, and following this method, left becomes the root of the tree, and the node at left is raised one level, and the node at left right does not change level, and the local root right is lowered one level. Now local root is set to the new root. So this is just like the example we watched. And that brings us to the end of this Slidecast.